There's a special case of the Fourier transform that's really worth considering. It's referred to as the DC component. DC means direct current coming from electricity, um, meaning a component of your electricity that's not oscillating is just always there at the same value. So the DC component in signals just means any constant value. Okay, but here's what I mean. Let's take a look at, I want you to realize that that the following integral of any signal, just integrate from negative infinity to infinity. Okay, I'm not taking absolute value, I'm not squaring, it's just the integral. That this is given by the Fourier transform. If it was convenient, if we knew the Fourier transform of x of t, then we don't even have to do any work to know what this integral is. Notice that this equals the, if I want, I can put something in there that'll make it more obvious. I'm going to put e to the negative I 2 pi 0 t dt. Now, why is that equal? Well, because everything inside this here is 1. Okay, so I've just rewritten it, but I've written 1 in one crazy fancy way. The reason I did that was so you could see that the Fourier transform equation gives us this answer. This equals x evaluated at frequency 0. All right, it's a nice thing to remember that also, of course, the opposite direction is true. X at time 0 is the same as the integral of the entire frequency domain, x of f df. Okay, of course, other values are also integrals. The Fourier transform is simply an integral representation. You know, it's just a set of integrals. So if any of those integrals were important to you, like for example, if you for some reason needed to know what is x of t e to the I 2 pi times 3 times t. All right, you need to know what that is? Well, of course, that's x evaluated at, in this case, -3, because I forgot the negative. Okay, so the Fourier transform is simply defined as integrals. Therefore, if you happen to need one of those integrals, you can look it up by its Fourier transform. The ones you'd encounter most often is just the integral of an entire signal. That's given by the Fourier transform at 0. Okay, and this opposite case. Okay, so this is referred to usually as the DC component. It's the zero frequency component of a signal. All right. Let's give an example. If you want to know what's the integral from negative infinity to infinity of sinc of t dt, again, sinc is the fun example because we know it's Fourier transform. We figured it out in a very simple way by using the its counterpart, rect. Rect is easy to integrate, so we could establish that Fourier transform relationship, and now we know all sorts of interesting things about this strange sinc function. In particular, that's going to be rect at 0, which equals 1. So we know that this sinc function, which is so nice, right? It was already nice because it crossed 0 at every integer. All right. It had a height of 1. It crossed at 1, 2, 3, 4. I mean, it's super nice signal because it has a nice Fourier transform, but also its integral, the integral here, of course, negative parts subtracting from the integral, that integral is 1. Okay. Now we also saw from Parseval's theorem that the energy of sinc of t equaled the energy of rect of f, which also happened to equal 1. So it's super nice signal. So next I'm going to actually use this property to actually calculate to prove Parseval's theorem. So here's how I'm going to do it. It's kind of a roundabout way. I like this proof, and I also imagine it's going to give you new ways of thinking about, just to make sure you understand how these Fourier transforms work. So consider the following. I'm going to write the energy. Consider what happens if I take x of t and convolve it with x of negative t. Okay? by the formula, that should be negative infinity to infinity, x of tau, x of negative, and then I plug in t minus tau, t tau, okay? Now, if I take the result of this convolution and evaluate it at time 0. So this is an entire signal, right? You do a convolution of x with it itself flipped backwards. I forgot one thing I wanted in this example. I actually want the one flipped backwards to be the conjugate. So that's a conjugate. Sorry about that. Sometimes I think of these signals as real and I forget to add the conjugates. So take x of t, convolve it with itself flipped in time, and conjugate it. Seems like a weird thing, but believe it or not, there's a name for this this type of convolution. This is called the autocorrelation function. So it actually is something that you encounter in signal processing. Okay, it's actually somewhat important. But forget it. We just need it for this equation. We say, what does that equal? It equals this thing. But now I want to look at this whole output signal, the autocorrelation function, and only look at it at time 0. Okay. And it turns out that the autocorrelation function at time 0 equals, well, I just plug in 0 for t, integral negative infinity to infinity, x of tau, x conjugate of, and now it's tau. D tau, but x times the conjugate is the absolute value squared. So equals negative infinity to infinity, x of tau squared d tau. All right, so that is the energy of x of t. So what we've realized here is that this weird autocorrelation function, if you evaluate it at time 0, you get the energy of your signal. And that's an important property of the autocorrelation function. We're not going to get into autocorrelation functions. We're not going to use them here in this class. But we see that at least when you evaluate at time 0, you get the energy. Why is this useful for our proof? Well, because let's look at what this is in frequency domain. Frequency domain. So we take a Fourier transform of the autocorrelation function. Okay, so Fourier transform of autocorrelation function. Okay, equals Fourier transform of x of t, x convolved with x conjugate of negative t. Well, convolution property says that that becomes multiplication in the frequency domain. So Fourier transform of x of t times Fourier transform of x conjugate of negative t. Now, do you remember the conjugate rule? Of course. So the conjugate rule says that this is, we have a name for the Fourier transform of x of t, just x of f, but this one is just x conjugate of f. There's no negative f because of the conjugate rule gets rid of the negative. So this equals the magnitude of x of f squared. So that is cool. The Fourier transform of the autocorrelation function is the magnitude squared of the Fourier transform. Good. So we're almost done, because now we're saying that the energy equals this thing evaluated at time 0. So if we want to know something in the time domain at time 0, the rule we just learned up here is that at time 0 in the time domain is the same as integrating in the frequency domain. So let's go use that here. Energy equals time 0 of the autocorrelation function. In the frequency domain, that's the magnitude squared. So the energy, therefore, energy of x of t equals the integral negative infinity to infinity. So f squared df, and that's the Parsifal's theorem. I want to say one more thing while we're on the subject of DC components. It's important also to know, now that we have these delta functions, we start to realize that we can take Fourier transforms of delta functions, and I want to just say delta functions There's a relationship. There are some observations we should make when we're looking at delta functions as signals, because they're sort of make-believe signals. And because of that, we get some anomalies. For example, we already saw that delta of t goes to 1 in the frequency domain. You just apply the Fourier transform integral to verify any properties, any pairs of Fourier transforms that have delta functions in them. You can only verify them using the integral that starts with the delta function and goes like in the direction of this arrow here. In other words, you can plug in delta of t into the Fourier transform integral and you can get back 1. You can't verify it backwards, unfortunately. You can't plug 1 into the inverse Fourier transform integral and get back delta t. It's just not going to happen. There is no function delta t, so it just doesn't work. But we still say this is a Fourier transform pair, and it's easy to confirm it if you start from the right direction. Okay. In more general, if we did t minus some shift, cap t, I'll make that tau, then we would get, of course, anytime you shift, we have a shift rule, right? Anytime you shift, you're always going to get e to the negative I 2 pi tau f. Okay, that's just multiply that phase by the previous signal. Okay, so by duality, you can imagine we would also have these types of properties. In the time domain, if our signal was a constant, then in the frequency domain, it's delta of f. And of course, you know, you can make this more general. If that was some constant c, then it's just going to be c times delta f. Okay, so constant signals, this makes a lot of sense. A constant signal, it's just flat everywhere. It's a delta function at frequency 0. So it only has a 0 frequency component, no other frequencies, nothing's oscillating here. And similarly, if you have a complex exponential, e to the I 2 pi ft, this is an exponential at frequency f. So intuitively, and also can be confirmed, the Fourier transform is simply delta of, oops, I don't want to use little f because I'm using little f as my variable in the frequency domain. I'm going to use a different letter here, capital F. That's going to be delta of f minus capital F. So it's going to be a delta function in frequency. Here's 0, here's capital F. It's going to be this type of thing in frequency, because in time it's a complex exponential. So sine or cosine then splits into two complex exponentials. So let's say cosine of 2 pi ft goes to, well, by splitting it up with Euler's identity, we get a 1/2 delta of f plus cap f plus 1/2 delta f minus cap f. This would be, split that into Euler's identity and then use the above rule. So in the frequency domain, it looks like this. 0, we have f, we have negative f, and this goes to 1/2. Of course, if the cosine was scaled, this would scale accordingly. If the cosine had a phase shift, we would get phases on these. If it was a sine, which is just a phase shifted cosine, this is one of these will be times I, this one will be times I, that'll be times negative I. I think it's that way. Again, just use Euler's identity and the above formula. So this is very intuitive, yet you cannot plug either of these into the Fourier transform integral. They are periodic. They are not finite energy signals. They will break the Fourier transform integral. You have to basically memorize these because they're very intuitive. They need to be memorized. But secondly, you can verify them by plugging any of these into the inverse Fourier transform integral, and the result is the sifting property, which is extremely easy to use, and you get back these answers. Now remember, what does Parseval's formula say? It says energy should be the same in time and frequency. Well, let's just check. Energy in time, infinite. This has finite power, but it has infinite energy. Energy and frequency. Oh, remember we said the energy of delta is infinite. So, okay, at least that's matching up. So here, this fact here. Let me get a color. The fact that constants are delta functions at time 0. This we call it's a DC component, but I like to call it DC offset to set it apart from what we were talking about moments ago. This is saying your signal actually is all lifted. Like, imagine you start with some signal that we like, a finite energy signal, okay? Like, sinc of t. Fine. Sinc of t, we said above, the DC component is just evaluate the Fourier transform at 0. Nothing wrong with that, because the Fourier transform of sinc is rect, right here. And rect evaluated at 0, that's no problem. It equals 1. Okay, right here. So that's, this is straightforward, correct usage of the Fourier transform DC component rule. It's saying the integral in time, assuming it was finite, if it wasn't finite, you wouldn't get a finite answer here. It's the Fourier transform evaluated at 0. Now, in this case, we have a different. Suppose that you add a constant to sinc. Okay, you add a constant to sinc everywhere. It no longer is going to have a finite integral. What you've done by linearity, if you add a constant, you've added a delta function into the frequency domain at frequency 0. So now it doesn't make sense. What are you going to get if you evaluate the Fourier transform at frequency 0? Well, there's a delta function there now. It's going to be infinity. Just like the integral in time is now going to be infinity. Okay, so sometimes what you're going to have are like mixtures in frequency. You have something that looks like this. You have like some finite parts, okay, and you also might have a delta function. And this means that in the time domain you have a combination of some simple finite energy process, okay, that corresponds to this smooth part. Plus, by linearity, you also have these complex exponentials. And if you have one of those delta functions sitting at 0, that means you have an offset, that everything, your entire signal is lifted by whatever that amount is, c. On that delta function, the whole signal is lifted by c. It's not centered at 0 anymore. It's centered above 0, whatever the value of c is. Okay, so I think of this as having a different sort of name. It's a DC offset. You've offset the whole thing, whereas the DC component was just whatever the integral would have been. The DC component is only well defined if it's actually centered around 0 so that the integral converges.